So this is a very brief presentation, so we've only got 9 slides or so. So essentially what I'm discussing here is the design and implementation of remote undergrad electronic engineering laboratories. So Caroline and Colin Fitzpatrick are my academic colleagues in the Department of Electronic Engineering at the UL. So first of all, now I know this is probably quite different to most of the presentations in the sense that it's dealing with quite detailed engineering type content. But by way of introduction, engineering modules often, not always, have significant laboratory content. And the whole idea, of course, having laboratory content is that engineering, of course, is a practical discipline, but underlying that practicality are a lot of very detailed mathematical concepts. So the laboratory content is complementary to and also aims at understanding quite often what is very advanced and difficult to understand theoretical material. Now, usually, lab experiments are carried out in on-campus laboratories. So students come into a lab and they do the experiment and then go away and perhaps write up a report. Now, obviously, because of COVID, we haven't been able to have real-time on-campus laboratories. Now, in fact, in the last year, that is, the situation basically was where students could be on campus perhaps 1 week and then off campus the second week and so on. So they've had a second experiment perhaps on the university campus. In this particular semester, all of the labs have had to be carried out remotely. Now, indeed, in some cases, labs were actually cancelled. So there definitely is a need now to develop experiments that can be carried out remotely in the student's own time, within, of course, reasonable restrictions. And this approach, as I've seen myself and my colleagues as well, has some challenges, but we've seen that it does have great potential to enhance the whole student learning experience in ways that we didn't necessarily foresee in the first place. So in terms of my actual talk, I just want to give some brief points here as to what I'm going to cover. I'm going to first of all just explain the typical structure of an engineering module. This is perhaps indicative of any engineering module. I'll also discuss the lab work scenario that we have in pre-COVID times, which in fact our COVID situation may continue on to what we're going to do in the future. And based on our experiences with the COVID lab work scenario, I just want to discuss a possible new paradigm for student experiments, remote experiments that is, and their implementation in terms of optimizing, hopefully, the student experience. And then I'll present some brief student feedback, and also then, from our own departmental perspective, what future plans we may have to implement remote laboratories. So that's the basic outline of the presentation. So I just discussed one particular module. In fact, it's my own third-year electronics engineering module, which is on telecom fundamentals. Again, I'm not going to go into too many technical details here, but essentially it covers the theory of analog and digital communications. And as you can well imagine, there are very challenging theoretical concepts in this with a high mathematical content. You should bear in mind that perhaps compared to say 5, 10, 15 years ago, in my experience and quite a few of my colleagues, the students don't quite have the same mathematical background that we'd like them to have. So we certainly have to adapt our courses to reflect that reduction quite often in mathematical ability, which also may be linked to the fact that the points for engineering courses, as in my own department in particular, have come down a bit. And then along in this module also, we have, of course, experimental work, which is aimed at understanding the principles of communication system design and analysis. So here's typical module structure. So one will start off, of course, with an introduction as to the overall concepts of telecoms in this case. In this module, there are 4 main, what we might call functional blocks, to put a communications terminology on it. We start off with signal analysis, which is a very mathematical techniques for looking at real world communication signals. Now, backing up that, we'll have a lab. Into that, then we follow with a concept called amplitude modulation, AM radio basically, which also has a lab. That feeds into then frequency modulation, FM type systems, which also has a lab. And finally, there's quite a bit of work spent on digital communication systems, which also has a lab. Now, usually in my case at least, those 4 labs, the reports and so on, and the lab will consist not just of a basic laboratory experiment, but also pre-lab problems which enhance the understanding of both theoretical and the laboratory work. So the entire 4 labs there will cover 30% of the module assessment, and then usually in non-COVID times there will be a final assessment which will account for 70% or so of the exam. Now, what's happened this year in COVID times, I've had to have 2 separate assessments due to time constraints with SULIS, and the problem there is, and also with the laboratory experiments, that there definitely is, although it's hard to quantify, a certain amount of cheating, copying going on. So I've seen in marking those scripts that some scripts had almost identical, quite often wrong answers, in fact. So I think this is something that going forward, that if things are going to become more online in terms of assessments and so on, that the whole problem with plagiarism, copying is going to have to be an issue that's going to have to be faced up to. In any case, there's the typical module structure. Now, in terms of lab work, in pre-COVID times, and we may not go back to this overall scenario, essentially what happens is the students will go into a lab for a particular 2-hour session. We have a workstation. So in this case here, we have components like an oscilloscope, voltmeter, power supply, circuit prototyping board, and other equipment. And typically per workstation, we have 2 to 3 students carrying out an experiment. We would hope that they would have a pre-lab problem completed before they actually do the work, but that's not always the case. And within the lab, they would have technician and academic support. And a big benefit here is that there's also peer-to-peer interaction. Now, a typical workbench here, the equipment would cost maybe 4,000 or 5,000 euro, and maybe 30 of those particular workstations in a given laboratory. So the cost is not insignificant, and bear in mind that equipment breaks down and has to be replaced and so on. So there's quite a high cost associated with these labs. And indeed, I'm sure in other engineering departments, the costs perhaps are even greater. So very expensive equipment. Now, there are some disadvantages with this scenario, which has been basically the scenario since time immemorial, is that the students do have limited time to carry out an experiment. A lot of students may actually prefer to do experimental work in their own time. So for example, at weekends, where they can show a little bit of creativity, relax a little bit, have a bit of flexibility in how they approach the experiment. And also, especially when there's 2 or 3 students per workstation, I have seen in a lot of colleagues as well, that some students tend to be disengaged. You may have a strong personality essentially taking over the experiment. You may have some other students who are not confident of actually getting stuck in with their other students. And some students, I think, sometimes have maybe social difficulties as well. So it's not an optimum scenario quite often, having to have on-campus laboratory sessions. Now, because of COVID, there is a potential for a new paradigm for carrying out student experiments remotely. Now, we can't expect students to have 4,000 or 5,000 euro of equipment in their houses. But what's happened really over the last 5 or 6 years is that there are now many types of very sophisticated, low-cost electronic modules available. Not just basic components, but modules, 2 of which I just want to describe very briefly now. So here on the left-hand side, that little device on top is basically what's called an Arduino Nano microcontroller. And it's actually essentially quite an advanced microprocessor, which can be used as an advanced, indeed programmable subsystem, programmable by a laptop computer, for example, in electronic circuits. So it can be used to carry out very sophisticated digital and analog electronic experiments. It only costs €8. So it's effectively zero cost. And all the other components on that board are very inexpensive as well. So that particular fairly advanced experiment would have cost maybe, in terms of components, of maybe €10. So extremely cheap. Here's another component, in fact, a module, which has only become available over the last 4 or 5 years. And in fact, it's a handheld device. It's a full test and measurement module. It's multifunctional, programmable, controlled from freeware PC software and very easy to use. And there on the right-hand side, in fact, is a display on a computer showing very complicated signals and analysis of those signals. Now, that basic device, which 3 years ago would have cost €400 per device, now it's come down to maybe, from an educational point of view, about €250. And in fact, that €250 device would replace, has more advanced functionality and is more reliable than all of those components and equipment that we saw earlier on, which cost €4,000 or €5,000. So that handheld device basically has a capability for students of having their own laboratory at home. So that's this is a huge development really in low-cost advanced electronics. So really what that module has, you will require component or equipment that would have cost 10, 15, 20, 30,000 euro 10 years ago. So it does open up the possibility of innovative solutions to enable remote experimental work with all the consequent advantages. Oops. Now, in terms of actual real-world implementation, what's happened this semester in particular is that students at the beginning of the course will receive the electronic modules, some free and some requiring a deposit, so we can get them back, and also components specific to each experiment. So a little, basically a pack. And then each experiment to be carried out, obviously at different particular times during the module delivery, is essentially backed up by a comprehensive SULIS site for the module. And on the SULIS site, we have the experimental description, including photographs, explanatory videos if need be, links to the necessary software, which is all freeware, and then also students would submit the reports online as well, and also get feedback online from those reports. So the SULIS capability is very good in terms of supporting the offline experimental work. Now, what we had, in fact, in the last semester last year was that we had a 2-hour slot where every second week, in fact, during the first COVID situation, is that students did get in-person technical assistance and were able to meet other students. And that was especially important for first year. So some experiments were carried out on campus and some were carried out off campus. This semester, in fact, all of the experimental work had to be carried off campus. So, of course, that has an associated challenges with how to deal with that. And teamwork was encouraged in the sense of, especially via SULIS forum-based cooperation, but the emphasis really is on individual effort.
2 minutes, Michael.
Okay, thank you. So it is important that students do the pre-lab problems and do the experimental work with all the associated problems that can arise from that, essentially as an individual engineer. But peer-to-peer interaction is not ruled out. Now here's some student feedback. This is just some first years on those remote labs. One of which was using the kit was very smooth. First few weeks were a little bit problematic. That was less the case for second and third year, fourth year students. Important that lecturers respond quickly to emails. They felt that they learned quickly because they had lots of clear instructions. A lot of satisfaction in building circuits themselves, and they learned to actually enjoy it, which is not always the experience where you have a limited online campus, or rather on-campus experimental work. They developed their confidence, and they liked not having to submit reports every week, so they could come back to a previous lab and redo it or improve it after learning or figuring out something new. But it is important that you have a good workspace at home, and that may not always be possible. And in fact, there was almost no negative feedback from second and third year students, which is quite remarkable, in fact, really. So, final slide here, future plans from a departmental perspective. Next term, we do plan that for some individual modules, that some labs will be on campus, some off campus. We'll have off-campus labs and also a timetable 2-hour slot whereby students can come in to maybe access more advanced equipment and get technical and academic support. And then in the medium term, we will see, and finally here, the first year has been given the test and measurement kits for the duration of their degree, and then have more interlinking between all of the electronic module streams that utilize the kits and also have common modeling software, which in fact is currently not the case. So lots of modules actually quite distinct from each other, but we do need to certainly improve how first year modules interact with second year modules and so on. So in summary, this whole idea of having offline labs where students have a lot more flexibility, I think offers a very good potential for improving the overall student experience. And that's basically it. So thank you very much.
Michael, thank you very much. Again, very interesting.